1,000 feet below the surface, there is no sunlight, no quick ascent, no emergency swim to open air. At that depth, the ocean is not simply dark. It is pressure, it is cold, it is isolation. And for saturation divers living and working under extreme pressure, the surface can be days away even when it is directly above them. Tonight on Deep Sea Crisis, we are going inside one of the most dangerous working environments on Earth. A saturation diving operation nearly 1,000 feet below the surface. A steel diving bell, a pressurized living chamber, a team dependent on hoses, valves, gas systems, electrical power, communication lines, and men on the surface they may never see during the entire job. And then something goes wrong. The lights fail. Communications disappear. The bell stops responding. And far below the ship, two divers realize that their connection to the surface may be dying. To understand why this is so dangerous, you first have to understand saturation diving. Most recreational scuba divers remain underwater for minutes, maybe an hour. They descend, they complete the dive, they ascend. Their bodies absorb increased amounts of inert gas as pressure increases, but within carefully planned limits they can return toward the surface through controlled ascent procedures. Saturation diving is completely different. When commercial divers must work at extreme depths day after day, repeatedly decompressing after every shift would be inefficient and dangerous. So instead, they remain pressurized. For days, sometimes weeks, the divers live inside sealed chambers aboard a ship or offshore platform. Those chambers are maintained at approximately the same pressure the divers will experience at their working depth. They eat there, sleep there, rest there, talk there. Everything happens under pressure. The divers are transferred from the living chamber into a diving bell without returning to normal atmospheric pressure. The bell is then lowered through hundreds of feet of water to the work site. At the end of the shift, they return to the bell. The bell rises. It locks back onto the pressurized chamber system, and the divers go back inside, still under pressure. Only after the entire rotation is complete do they begin the long decompression back to normal atmospheric pressure. That process can take days. This means something unsettling. A saturation diver may finish his final underwater job on Monday, but still not be able to walk outside into normal air until Thursday or Friday. Pressure has changed the rules. At 1,000 feet, the pressure is enormous. Every piece of equipment matters. Every seal matters. Every valve matters. Every human decision matters. Because the deeper you go, the fewer ordinary solutions remain available. Our scenario begins aboard a commercial diving support vessel holding position over a deep-water industrial site. Below the ship sits equipment that requires inspection and repair. Pipelines, valves, steel structures. Equipment designed to operate in an environment humans were never meant to enter. Inside the saturation complex aboard the vessel, three divers prepare for another shift. They have already been living under pressure for several days. Their voices sound different because of the breathing mixture. At extreme depth, ordinary air becomes unsuitable. Nitrogen can cause severe narcosis. Oxygen itself becomes dangerous at excessive partial pressures. So deep commercial diving commonly relies on carefully controlled gas mixtures, often involving helium and oxygen. Helium changes the voice. It changes heat loss. It changes how sound travels. It changes how the body feels. But to these divers, it is part of the job. One diver will remain inside the bell as the bellman. Two will exit to perform the underwater work. Their equipment is checked again. Helmets, umbilicals, hot water suits, breathing gas, communications, emergency gas, tools, lights. The bell hatch is closed, the bell separates from the chamber system, and the descent begins. The surface disappears almost immediately, 100 feet, 200, 300. Outside the bell windows, blue becomes black. 400, 500. The temperature drops. 600. 700. The bell continues downward on its cable. 800 feet, 900, then nearly 1,000 feet below the surface, the bell stops. The divers have reached working depth. There is no natural light. The water outside is completely black until the lamps come on. The diving supervisor on the surface gives the order. Diver 1 prepares to leave the bell. His helmet is secured. His umbilical is checked. That umbilical is his lifeline. It supplies breathing gas, communication, electrical power, hot water. Depending on the system, monitoring and other life support functions travel through or alongside that connection. The diver climbs through the bell hatch. For a moment, he hangs beneath it, a tiny human figure suspended in black water. Then he begins moving toward the work site. Diver 2 follows. The bellman remains inside. Above them, nearly 1,000 feet of ocean separates the team from normal atmospheric pressure. The work begins. The divers inspect the structure. They communicate with the supervisor. Their helmet cameras transmit images upward. Metal surfaces appear through the lights. Marine growth, bolts, pipe sections, valves. The job is technical, slow, precise. And for the first 20 minutes, completely routine. That word is dangerous. Routine. The environment is never routine. Only the procedure is. The ocean remains capable of turning a normal job into a crisis without warning. The first indication is almost insignificant. A flicker. Diver 1's light dims, then returns. He reports it. The supervisor acknowledges. Electrical readings are checked. Everything appears normal. The diver continues working. A few minutes later, the light flickers again. This time, Diver 2 notices his helmet system briefly cut out as well. Communications crackle, then clear. The surface team begins troubleshooting. Could be a connector, could be electrical interference, could be something affecting the supply system. The divers are told to pause. At 1,000 feet, small anomalies deserve attention. A light failure in shallow water may be an inconvenience. A system failure here may be the first sign that something much larger is going wrong. Then the entire work site goes dark. Both divers lose their primary lights at nearly the same time. For several seconds, the only illumination comes from the bell in the distance. The divers stop moving. Communications break into static. The supervisor's voice becomes distorted, then disappears. Now the divers can no longer clearly hear the surface. The surface cannot clearly hear them. Diver 1 signals with his backup light. Diver 2 responds. They are still alive. Their breathing gas is still flowing. That is the most important fact. For now. They begin moving back toward the bell. Every saturation diver understands priorities. Breathing first. Protection from the environment. Communication. Navigation. Return to the bell. The problem is that their umbilicals trail behind them through the structure. At extreme depth, the umbilical is both salvation and hazard. It keeps the diver alive, but it can snag, twist, become trapped, or become damaged. Diver 1 reaches a section of steel framework and feels resistance. His umbilical has caught somewhere behind him. He cannot see exactly where. His backup lamp illuminates only a small section of metal. He pulls gently. Nothing. He pulls again. Still nothing. He reports the problem instinctively, but the radio produces only static. The surface may not hear him. He looks toward Diver 2 and signals. Umbilical problem. Do not pull hard. Damage that line and the emergency changes instantly. The diver moves backward. He follows his own hose by hand. 10 feet. 20. Then he finds it. The umbilical is looped around a projection on the structure. He frees it carefully. 30 seconds, maybe 40. But at this depth, 40 seconds inside an emergency feels much longer. The two divers continue toward the bell. Then the hot water system begins to weaken. Saturation divers working at extreme depths are vulnerable to severe heat loss. Helium-based breathing mixtures conduct heat far more efficiently than air. Cold water pulls heat from the body. Commercial systems may pump heated water through specialized suits to help keep the diver warm. If that hot water supply fails, cold can become a serious threat. At first, the diver simply notices discomfort. The water inside the suit is not as warm. Then it becomes cool, then cold. The body begins reacting. Blood vessels constrict, muscles tighten, hands lose dexterity. The divers need to reach the bell. But now the bell has another problem. Inside, the bellman sees warning indications from the surface link. Power instability, communication failure, something affecting multiple systems. He tries to contact topside. No response. He checks the bell's internal systems. Emergency lighting remains active. Internal gas is available. The bell itself still has life support, but its connection to the ship is no longer behaving normally. Then the bell moves. Not much. A sudden sideways pull, then another. The bellman looks through the viewport. The bell is drifting relative to the structure. The vessel above may be moving. In deep water operations, a ship may use dynamic positioning systems to maintain location. Thrusters, navigation equipment, computer controls, position references. If a vessel loses station, the effects can be catastrophic for divers connected to the ship thousands of feet below. The bell is connected to the vessel. The divers are connected through umbilicals. The work site is fixed. The ship is not. If the vessel moves too far, the entire system can be stretched beyond safe limits. The bellman immediately attempts contact. Nothing. He looks outside. The two divers are approaching. Their lights move through the darkness. He signals them urgently. Return now. Diver 1 understands immediately. Something is happening to the bell. They accelerate, but speed underwater comes at a cost. Physical effort increases breathing demand. Breathing demand increases gas consumption. At this depth, the density of gas and the work of breathing are already significant concerns. The divers cannot sprint as if running across a parking lot. Every movement must remain controlled. Then diver 2 stops. He feels a hard pull through his umbilical. The line tightens. He turns. The structure behind him disappears into darkness. His umbilical is caught, again. But this time it is worse. The vessel movement has increased tension. The line is pulled against steel. He tries to move toward the snag. The tension becomes stronger. Diver 1 reaches him. The two men search the line with their lights. They find the point where it has become trapped around part of the structure. If the vessel continues moving, something will fail. The umbilical might break. Equipment could be torn from the diver. The diver himself could be dragged. There is almost no time. The two men work together. One controls the line. The other frees it. The tension increases. For several seconds, the umbilical is almost rigid. Then suddenly, it releases. Both divers move forward. The bell is now farther away. Not because they moved, because the bell has. The situation has changed from equipment malfunction to full survival emergency. Above them, the vessel crew is fighting its own battle. Positioning systems have malfunctioned. The ship has begun moving away from station. Emergency procedures are underway. Thrusters respond, then stop, then respond again. Technicians attempt to restore systems. The diving supervisor knows exactly what is below the vessel. 3 lives, 2 outside the bell, 1 inside. Every foot the ship moves may translate into dangerous movement hundreds of feet below. The supervisor attempts communications, still intermittent. Bits of sound break through. Return. Bell. Emergency. Then static. The divers do not need the full sentence. They know. Get inside. Diver 1 reaches the bell first. The bellman helps manage the umbilical. Diver 2 approaches seconds later. Then the bell shifts again. The lower hatch moves relative to the divers. Diver 2 reaches for it. Misses. The bell swings away. His umbilical tightens. Diver 1 grabs him. For a moment, both divers hang beneath the bell. The black water around them contains nothing recognizable. No bottom, no surface. Only the steel bell. The only safe place they can reach. The bell swings back. This time they enter. Diver 2 first. Then Diver 1. The bellman pulls the umbilicals inside. The hatch closes. The three men are now together. But being inside the bell does not mean they are safe. Their breathing gas outside the bell is no longer the immediate concern. Now the bell itself must keep them alive. The bell is essentially a small pressurized survival capsule. Emergency gas supplies, carbon dioxide removal, communication systems, heating, lighting. Everything has limits. If the surface connection cannot be restored, the bell may need to rely on onboard reserves. And three men inside a small steel chamber will gradually consume oxygen and produce carbon dioxide. The bellman checks the systems: pressure stable, internal atmosphere acceptable, emergency power functioning, primary communication still down. They attempt backup communication. Nothing. One diver looks through the viewport. There is only darkness. Imagine the psychology of that moment. You are inside a steel chamber 1,000 feet below the ocean. You know there is a ship above you. You hope the ship is still above you. You cannot hear the people aboard it. You cannot see the surface. You cannot leave the bell and swim upward. Even if you could physically swim 1,000 feet toward the surface, your body is saturated with inert gas. A rapid ascent would be catastrophic. The water above you is not an escape route. It is another hazard. The men are trapped inside the only environment keeping them alive. Then something strikes the bell. A heavy metallic impact. All three men freeze. Another impact. This one louder. The bell may be contacting part of the structure, or equipment may be swinging nearby. The bellman checks the gauges again. Pressure stable. No immediate flooding. No obvious structural failure. But every impact raises the same question. How much can the bell take? The vessel above is attempting to regain position. The bell handling team tries to control movement. Deep water operations involve enormous lengths of cable and hose. Commands given at the surface do not create instant precision 1,000 feet below. The system has weight, momentum, drag, current. The people above cannot simply reach down and grab the bell. They must work through machinery. And machinery can fail. Minutes pass. Inside the bell, time becomes psychological pressure. The men check emergency gas. They calculate survival duration. They inspect seals. They talk. Talking serves more than one purpose. Communication confirms everyone remains mentally alert. But unnecessary activity also produces more carbon dioxide, so they conserve energy, stay seated, breathe normally, keep calm. The same rule that applies inside a cave applies here. Panic consumes resources. Only now the resource is not merely one diver's cylinder. It is the atmosphere inside the entire bell. The temperature begins dropping. The bell's heating is limited under emergency conditions. Metal transfers cold. Hands become chilled. The divers remain in their suits. They try to preserve body heat. One man starts shivering. Another tells him to keep moving his fingers. But not excessively. Everything becomes a balance. Stay warm. Do not waste oxygen. Stay alert. Do not panic. Then the backup communication system produces a sound, a burst of static, then a voice, weak, distorted, but unmistakably human. The surface. The men answer immediately. For several seconds, neither side can understand the other. Then one message comes through. Bell, hold, recovering position. That may be the best sentence the divers have ever heard. The surface knows where they are. The vessel is still functioning. Recovery is possible, but possible is not the same as complete. The divers remain trapped. The ship must stabilize. The bell must be brought back under control. The lifting system must function. And the bell must eventually return to the pressurized chamber aboard the vessel. Only then will the divers be protected from the ocean. The ship gradually regains station. The bell movement decreases. Impacts stop. The bellman reports conditions. Pressure stable. 3 divers alive. Emergency atmosphere functional. Awaiting recovery. Then the ascent begins. Slowly, the bell starts rising. 900 feet. 800. Inside, the divers cannot simply celebrate. They are still pressurized. The bell must maintain its internal pressure during recovery. Unlike ordinary divers ascending through the water, these men remain inside a pressure-controlled environment. The ocean pressure outside decreases as the bell rises, but the pressure inside remains managed to protect the saturation team. 700 feet, 600, 500. The men listen to the machinery. Every vibration feels important. Every unusual sound demands attention. At 400 feet, communications improve. The supervisor tells them the vessel is stable. The bell recovery system is functioning. They are coming home. But home is not the deck. Their home is the saturation chamber. The bell reaches the vessel. It is brought into position. The transfer system aligns it with the pressurized chamber complex. This is another critical stage. The pressure inside the bell must match the chamber system. Seals must hold. Connections must be correct. Only then can the internal hatch be opened. The divers wait. Then comes the signal. Transfer pressure confirmed. The hatch opens. The men climb from the bell into the chamber. 1, 2, 3. The hatch closes behind them. They are safe from the immediate underwater emergency, but they still cannot walk outside. They remain under saturation pressure. Their bodies still contain dissolved inert gas. The vessel may be only yards from them now. Normal air may be on the other side of thick steel. But physiologically, the surface is still days away. That is one of the strangest realities of saturation diving. Rescue does not mean release. You can survive the emergency and still remain trapped by the laws of physics. The divers now begin another process. Medical checks, equipment review, system investigation, eventually controlled decompression. Slowly, very slowly. Pressure is reduced according to carefully managed schedules. Hours pass. Then another day. The men sleep, wake, eat, talk. The disaster becomes a story before they have even returned to normal atmospheric pressure. But the incident leaves questions. What caused the initial power failure? Why did communications disappear? What happened to the vessel positioning system? Why did the bell move? Could the emergency have escalated further? Investigations after saturation diving incidents focus heavily on systems, because disasters at extreme depth are rarely caused by one single dramatic failure. They often involve chains. A power problem affects communications. Communication loss delays decisions. Positioning problems create movement. Movement tensions the umbilicals. Umbilical tension endangers the divers. Divers rush. Rushing increases breathing demand. Heat support becomes unstable. Cold reduces dexterity. Each problem feeds the next. This is called an accident chain. Break one link early enough and the disaster may never develop. Ignore several links and suddenly everyone is reacting to something far larger than the original problem. That is why redundancy is built into saturation diving. Backup power, backup gas, emergency communications, reserve life support, standby divers, hyperbaric rescue systems, detailed emergency procedures, because nobody working at 1,000 feet can depend on a single system. But redundancy does not remove risk. It buys time. And time is the most valuable commodity in any deep-sea emergency. There is another problem saturation diving teams prepare for. What happens if the ship itself must be abandoned? Consider the terrifying possibility. A fire aboard the vessel, explosion, collision, loss of stability. The crew on deck may be able to launch lifeboats, but the saturation divers cannot simply open the chamber door and leave. Doing so would expose their pressurized bodies to normal atmospheric pressure far too quickly. So some systems use hyperbaric rescue chambers, or lifeboats. Essentially pressurized escape vehicles designed to evacuate saturation divers while keeping them under pressure. Imagine escaping a sinking ship inside a sealed pressure vessel because the atmosphere outside could kill you. That is the world these divers work in. At extreme depth, pressure becomes part of your life support system. It is simultaneously the thing threatening you and the thing keeping you alive. After several days, the 3 divers from our scenario finally complete decompression. The chamber pressure reaches normal atmospheric conditions. For the first time since the operation began, the outer door can open safely. Fresh air enters. Real air. Not carefully controlled chamber gas. The men step outside. They see daylight. They feel normal atmospheric pressure. They can walk onto the deck. The ocean beneath them looks completely different from up here. Calm, blue, ordinary. Nothing on the surface suggests what happened 1,000 feet below, and that may be one of the most deceptive things about the sea. The surface can look harmless, while an emergency is unfolding in complete darkness underneath. Saturation divers work in a world most people will never see. They repair infrastructure, inspect underwater systems, cut steel, operate tools, solve mechanical problems. And sometimes they do it at depths where ordinary scuba diving is impossible. They rely on technology, but ultimately, they also rely on each other. The diver trusts the bellman. The bellman trusts the supervisor. The supervisor trusts the technicians. The entire team trusts the engineers who design the system. At 1,000 feet, survival is a chain of human beings and machines. If that chain holds, the diver comes home. If it breaks, there may be very little room for error. The lesson from this scenario is not that saturation diving is reckless. Modern commercial diving operations use extensive planning, training, and safety systems precisely because the environment is so unforgiving. The lesson is that extreme depth survival depends on preparation long before an emergency begins. Backup systems must already exist. Gas reserves must already be available. Emergency plans must already be understood. Divers must already know what to do when communications disappear. You cannot begin preparing for a 1,000-foot emergency after the lights go out. By then, preparation is over. Now you are surviving. 1,000 feet below the surface, courage matters. But courage without procedure can become panic. Equipment matters. But equipment without maintenance can become another failure point. Technology matters. But technology without trained people cannot rescue anyone. The ocean does not care how expensive the vessel is. It does not care how advanced the computer system is. And it does not care how many successful dives came before this one. Every descent begins again at zero. Every valve must work. Every seal must hold. Every decision counts. Because at 1,000 feet below the surface, there is no quick way home. There is only the system, the team, the bell, and the thin connection stretching upward through nearly 1,000 feet of black water. This has been Deep Sea Crisis. Next time, we go into another environment where the surface is close enough to imagine but impossible to reach. A diver enters a wreck. Behind him, rusted steel. Ahead of him, darkness. Then the passage collapses, the guideline disappears, and a ship that sank decades ago becomes a trap all over again. Until next time, respect the depth, trust the plan, protect your breathing gas, and remember, the deeper you go, the smaller your margin for error becomes.